ends up being approximately equal to beta delta. This is called a small angle approximation. Okay, this was to show this kind of like where we're going with this idea is that, so this ends up being, it gets rid of the tangent of beta, so you just get J Z0 B delta. And since Z0, in the special case of a lossless transmission line, Z0 is equal to square root of L over C. And so we just end up with JWL delta as the impedance of the line looking in. So what does that look like? Well, that looks like a purely, just an inductor, right? There's no, the impedance of an inductor, if you guys remember, so if you have a purely inductive load, so purely inductive, looks like the impedance of an inductor looks like J omega L, and the impedance of a capacitor looks like 1 over J omega C. Are you guys familiar with that? Okay, so this guy also, if I just look at this guy looks like minus J omega C, because, over omega C, I'm sorry. It's because 1 over J is equal to minus J. Okay, so if you have a load that's purely, an inductance, an impedance, if you have an impedance that's purely imaginary, if it's purely imaginary, then it's either purely inductive or purely capacitive. Okay? If it's purely inductive, you'll have kind of a positive J omega L. If it's capacitive, you'll have a minus J something. Okay? So the fact that after we put a stub here next to this short on this transmission line, and we ended up with J omega L delta. Remember, this delta is this length, and all we're saying for the length is we're saying it's short. It's short enough that tangent of beta delta is just equal to beta delta. So to do that, we get a purely, this looks like a purely inductive load, this short stub that we added. And by changing the length delta, we can tune that inductance. I can get, if I just have some transmission line made out of a characteristic impedance that has an inductance per unit length of L, I can just get different lengths of that transmission line, short the end, and by changing that length, I can get different inductances. Okay, so if I draw that on a line, let's say I'm changing beta L, which is that length, times the beta, I can get basically tune the inductance. The reason this is purely inductive here is that it's positive when I'm drawing JSC. It's positive, so, and then I can basically change the value. The value is basically the inductance of this thing. Okay. Another thing as a reminder, or something that it's worth emphasizing, is lengths in transmission line. L is a length in centimeter, meter, inches, whatever. It's actually a length, right? We're always saying that length, whenever these equations happen, is the actual length we have in these equations is beta times L. Beta is 2 pi over lambda. Lambda is the wavelength of the signal going through. So remember all that. And the wavelength is dependent on the frequency. Do you guys understand why that's the case? Yeah. When you're looking at like so when you're looking at a transmission line, okay, let's think of three different cases. You have a completely matched transmission line, means that the characteristic impedance of the line, the load is the same as the line. That way you don't get any standing waves, you just get like sort of signals going through. As soon as you get either a short circuit on the end or an open circuit on the end or anything unmatched, you actually get a standing wave in the transmission line if you're giving it a purely single frequency. That means if you're poking along the line, you're gonna see like A voltages that looks like they're just sitting there and not moving, like a wave. It's almost like you've frozen the waveform of a combination of forward traveling wave and backward traveling wave. Okay, that means as you change, or as long as if you change the length where you're looking along that transmission line and looking at those voltages, at some point you're going to get repetitive patterns. Okay, you're going to get the same, you're going to get one maximum voltage, and you're going to get a minimum voltage, and you keep going back away from the load. You're going to get a maximum voltage and a minimum voltage, then a maximum voltage and minimum voltage. The period of that depends not just on how far you're going away in terms of centimeters, but how far you're going away and what is the frequency of your input. Okay, that's the frequency of your input is captured in beta, which is 2 pi over lambda of the wavelength. And the actual length is L. So we're always, when you're looking at this stuff, we're plotting beta L. And the beta L, because beta is 2 pi over lambda, the wavelength has units of distance. L has units of distance. This beta L doesn't have, there's no units there. Okay, so it's given in radians. There's no meters here, but it's length, essentially, at a given frequency. Does that make sense? No? Okay. Well, I mean, it's just, that's why I'm trying beta and then jamming L. So anyway, so at some point, we're going to look like an inductor. And then what happens is, as this length gets longer, at some point you're going to look like, because of this tangent of beta, this tangent function, a tangent looks like this. It goes from plus infinity to minus infinity repeatedly in this sort of a pi period. So you're going to go from a purely inductive load at some point to a purely capacitive load. And then that purely capacitive load you can also tune with this delta, this length. And then at some point, when you make that length longer, you repeat this inductive load pattern again. So you get this, so this suggests sort of a punchline, suggests our punchline, which is this graph, as you'll see, is this thing that is like going around in the circle. As your lengths and impedance are going up, you're going to basically be getting different impedances along the circle. Okay, and this is the relationship between beta, 2 pi over lambda, and the frequency. So the group sort of velocity, or the phase velocity, is lambda f. And this will be the equivalent to the speed of light if you're in a vacuum. But it's kind of like those kind of speeds. You can think of this as being a very, very high speed. Okay? That's what you're going to typically run into. Okay, so the reason this is called impedance flow, again, it's trying to lead us to the Smith chart. The idea of calling it a flow is implying that it's this thing that's changing smoothly from inductance to capacitance and back as you're changing lengths, given a certain characteristic impedance, given a certain load impedance, given a certain frequency. It's this repetitive pattern of impedances that are changing. Okay. So what's next? Let's see, what else do I want to say? Okay, so let's now look at the equation again. So this equation for if you have a transmission line of certain characteristic impedance Z0 and a short circuit load, the impedance is plus J Z0 tangent of beta L. I'm just rewriting this equation up here, again, down here. So at this beta L is equal to pi over 2, this input impedance turns into infinity. So this is drawing that same equation. So it's just a function of tangent. Tangent at pi over 2 turns into infinity. Okay, so what has an infinite impedance? Huh? Sorry? Open circuit. So at some length, if you have a transmission line with a short circuit end, if you change the length, if you're basically either you're looking at different points along this, or if you change the length of this transmission line stub, it looks like you have an open circuit. And you're going from open, and then you change the length again for a while, it looks like you have a short circuit. And then an open circuit, and then a short circuit. So again, I'm going to write that down, because leading to this concept that this is a repetitive pattern. So this means a lossless transmission line with short circuit load will look like open circuit at some length. And that length is L is equal to lambda over 4. So the reason I'm saying that is because beta is 2 pi over lambda, and we want beta times L to equal, at beta times L equals to pi over 2 is when we get this event happening. So if I plug in 2 pi over lambda, L is equal to pi over 2, I end up with L is equal to lambda over 4. So at a given, and again, remember that lambda times the frequency of the input. So the wavelength times the frequency of the input is the group velocity. So as the wavelength changes of the signal, so does the frequency. So at some frequency, at some wavelength of the signal, given that value, at some length, and a short circuit would look like an open circuit. Okay, so at some lambda over 4, away from a short circuit, I'm gonna look like an open circuit. And it turns out that same thing happens if I go another lambda over 4. I'm gonna look like a short circuit again. So it's this repetitive pattern as you look along the transmission line. Okay, so this is just an important concept that'll come in really handy while we're looking at the Smith chart. All right. You guys need time to take this down? You good? So let's start looking at the Smith chart now. So the Smith chart has got a really long history, and it's interesting that it survived this long, but it's still, again, it's still used, it's completely like used all the time for transmission line analysis. So it was created historically by this guy Smith chart, and it was created in going back to like the 1930s for people to do these transmission line calculations. So we have these equations we worked over the last few weeks about. If you think about them, you know, we have V0, we have like I, we have all these different parameters, but really we're playing with just a couple of things. We're playing with impedance and reflection coefficients. Okay, there's the impedance of the characteristic impedance, there's a load impedance, there's a source impedance, and then there's the reflection coefficient at the load. But you know, if we put in another transmission line, we got a different type of reflection coefficient. There's like these relations. So that's kind of like what you have is you have those two factors. You have impedances and you have reflection coefficients. Okay, so the transmission line is a way of relating those two in a graphical way rather than doing the equation. So it's not doing anything additional compared to the equations we've been looking at, but it's a way of graphically representing those. Initially, when it came out, it also had the role of making it easy to do calculations. When you were doing a transmission line design, et cetera, you know, this is like 1940, they didn't even have like actual like calculators, right? There was like, I don't know what they had. They had like slide rules or something. Anyway, like just doing a tangent theta calculations that were like what we were doing for actual lengths was difficult. You couldn't just plug it into your computer and figure out what it was. So it was handy to have that. It doesn't really have that role anymore. So because it is now easy to do the equation calculations, but it's still the main importance is as a graphical aid to get a visual about how things are changing and where you're going. So it hasn't lost its value. It's really kind of a cool thing. But mostly now as a graphical aid. Okay, so where it sort of, the importance of it, let me just sort of build up to how derive it coming from the flow, and then we're going to look at a few cases of how it's used. Okay, so it's coming from the fact that there is a relationship between reflection coefficients and impedances. So in the special case of just at the load, so just at the load, we have the load reflection coefficient, which is Z sub L, which is the impedance of the load, minus the characteristic impedance of the line over Z sub L plus Z sub 0. So this is the reflection coefficient at the load. Okay, now, so again, that's at the load, but when we started, we just had the characteristic impedance of the line, and then we had the load characteristic impedance. Then we started defining something called the line impedance, which is the impedance anywhere along the line. Okay? So that means we can also define a reflection coefficient anywhere along the line. Okay, so just like we had, so we went from z sub L, z sub 0, z sub source, and then we kind of like came up with z line, meaning anywhere along the line we could do it. We could also kind of just from going from just having z sub L, look at gamma sub line anywhere along the line. And the definition of that anywhere along the line is that at any point along the line, at any point gamma z, so at the load, so the load coefficients definition was really V0 minus at the load over V0 plus. So this told you that, you know, the reflected voltage is some multiple of the transmitted voltage. Okay, this was the definition of the load impedance. Sorry, that was a load reflection coefficient, right? So the same thing, I can define a reflection coefficient anywhere along the line and then have it give me the relationship of V0 plus over V0 minus over V0 plus at any point along the line. Because these have values anywhere along the line, not just at the load. So I can also just define a reflection coefficient anywhere along the line. And generally, okay, all these reflection coefficients can be complex. Okay, so this is the concept of, let me write this down. So this is, what should we call this? Let's call this line reflection coefficient. So this is concept one. Second, I don't know if it's a concept, but it's like just something to keep in mind, is if you look at the load reflection coefficient or any reflection coefficient, that's the equation for it. And, you know, in general, we're kind of looking, not kind of, we've talked about lossy transmission lines, but to make life easy for ourselves, we keep going back to the lossless transmission line. So for a lossless transmission line, Z0s are real, purely real, but Z sub L at any point, it can be a complex number. We've never taken that off the table. In fact, in the problem that I've given you guys, the Z sub L looks, you know, it's got an inductor and it's got a resistor and so on. So it's a complex value, okay? So Z sub L in general is complex. Is complex in general. Meaning that gamma sub L is also going to be complex. So, yeah, okay. Don't want to keep repeating myself. So we can write gamma sub L as there's a real component. So I'm going to say gamma sub L sub R for the real part of gamma sub L, and an imaginary component for gamma sub L I. Okay, that's one way to write a complex number. So that's what's called rectangular coordinates. And the other way to write the same thing is in polar coordinates, which is an amplitude for gamma sub L and a phase angle. So by this, so these are the same way. So this is rectangular coordinates, this is polar coordinates. But they're both representing the same thing. So if I had this, if I'm in the complex plane and I have, you know, the real part of gamma, which is equal to gamma sub r, and then I have the imaginary part of gamma, which is gamma I, and I have a point along this somewhere, I can either write it as, you know, gamma, so this would be in polar coordinates, I would have like a gamma sub r and a gamma sub I, and I would write it like this. Or I can draw a vector from the origin, oops, that wasn't a very good vector. And say the amplitude is gamma sub L, and then there's a phase of phi sub L. And that would be writing it like this. So it's defining the same point in the complex plane. It's just I can write it either in rectangular coordinates or in polar coordinates. Okay, so this is concept 2, which is rectangular or polar coordinates what should I say? You can go back and forth between them. Okay. So you can, that's the second concept, is to keep in mind. So these three things will all add up to the Smith chart, as you'll see. Okay, the third concept is that in a Smith chart, all the impedances are normalized to the characteristic impedance of the line. So this is concept 3, is all impedances in Smith chart are normalized to z sub 0. So for example, if I write gamma sub L when it's normalized, like if I rewrite it, it'd just be z sub L over z sub 0 minus 1 over z sub L over z sub 0 plus 1. And I'm just going to call this guy z sub L over z sub 0, z sub L bar, or the normalized load impedance. So this is the normalized load impedance. So all the impedances you'll see in a Smith chart, you'll see like a number like 1 or less than 1, kind of as a realistic impedance. And this is equal to, and I can write gamma sub L in its complex form rather than just like this. I can write that as gamma sub L R plus J gamma sub L I. Okay, so we're going to basically start with these three things and derive the Smith chart. So again, we have a general reflection coefficient anywhere along the line. We have the complex numbers, the fact that we can write complex numbers either in rectangular coordinates or polar coordinates. And to make it easy for ourselves, we're also normalizing all the impedances. Okay, so let's start with that. So what is this saying? So notice that there is, like, always along the line, anywhere, not just at the load, but anywhere along the line, there is a direct relationship between the impedance and the reflection coefficients. Okay, so there's this functional relationship between them. Okay, and that's kind of what the Smith chart is giving you. And it's giving you a visual as these parameters change, like what that relationship is. Okay. So let's go back to this reflection coefficient and the anywhere along the line. So back to gamma sub z. So at any point in the transmission line, you're going to have a forward-going wave and a reverse-going wave. So at any point along the line, I've defined the gamma sub z is equal to v0 minus z over v0 plus of z, or the ratio of the backwards going wave to the forward going wave. So v0 minus is, so if I call v0 plus, remember v0 plus is, so that's sort of the shoot, I'm having a phasor, sorry, is v0 plus e to the minus j beta z is the forward going wave. So at any point along the line, v0 minus of z is equal to v0 plus of z e to the plus j beta z times this gamma L of z at any point along the line. So if I plug in the gamma L for this again, I'm going to end up with, so gamma of z, gamma L of z, is gamma sub L v0 plus of z e to the plus j beta z over v0 plus e to the minus j beta z. So the v0s cancel each other out. This guy goes on top, and you end up with gamma of z is equal to gamma sub L e to the plus 2j beta z. So this says the reflection coefficient anywhere along the line is the reflection coefficient of the load times a phase that's a function of where you are along the line. Okay, which is the same factor we saw here. Basically, you end up in a situation where at some point along the line, you kind of see the same load you had at the end of the line. So this is what's going on here, is you get this repetitive pattern. At some point, imagine if beta z is equal to 0, right? Beta z equal to 0 is either at the load or it's at a, beta z is equal to 0 is at the load, okay? And beta z is equal to sort of 2 pi, the same thing happens, right? In those points, you're just going to end up with gamma sub L. Sorry, pi. You're going to end up with gamma sub L. Okay, so and it kind of keeps coming back. Okay, so now let's look at the line voltage at any point. So the line voltage at any point, which is the sum of the forward going voltage and the reverse going voltage. That's the line voltage at any point. We can draw that, we can write that up in terms of the forward going voltage, e to the minus j beta z times 1 plus gamma of z. Just plugging this in. And the line current at any point, if I sum up the forward going current and the reverse going current, that is equal to V0 plus over Z sub 0 e to the minus j beta z 1 minus gamma of z. So these are still definitions. I also noticed that like this thing I was telling you guys that at some, let me write this in another way also. So gamma of z is gamma times L times this phase. If you think of just the absolute value of gamma sub z, this phase, the absolute value means, you know, we're getting rid of the complex part, like the imaginary part of it. So if I just look at the absolute value of gamma z, whoops, it's going to look like the absolute value of gamma L. So if I write gamma sub L, if I draw gamma sub L, so gamma sub z is gamma sub L amplitude e to the j to beta z plus phi sub L at any point. So this guy is the phase angle of phi sub L is phase angle of load. So drawing this in the, so if you draw this in the complex plane where we got the real part of gamma is again gamma sub r, and the imaginary part of gamma is gamma sub I. Just at the load, so for gamma, for let's say just at the load I had this gamma sub L and I have this phase angle phi sub L. So I'm just writing the reflection coefficient at the load. At the load in this drawing, the reflection coefficient in this complex plane. At the load, I'm going to be here. At z equal to 0. Guys with me? Okay. As I move away from the load, as now I'm physically moving away from the load, and I'm just drawing this thing again, my amplitude is not going to change, but my phase is going to change. My phase is gamma sub z. The amplitude doesn't change, but the phase is a function of z. It's starting at this point at the load. As I walk away from the load, it's going to start, this phase angle is going to start changing. But the amplitude won't change. So I'll be along this circle, that the radius is gamma sub L, and then this is going to start moving in a circle. So as I'm moving away from the load, that's what my reflection coefficient is going to do. The line reflection coefficient is just going to start walking along. Okay, so as I'm going along the load, it's going to, so as I'm changing beta sub z here, it's going to, remember that z, we've called z equal to 0, this is shorted or whatever, this is like z sub L, let's say, in this general case. This z is going to be negative, right? It's always, we've made z equal to 0 at the load. That's what we just called it in a frame of reference. And as we walk away from z, or z I'm plugging into here is a negative number. So as that negative number multiplies by b and adds this phi sub L, this is going to change in a clockwise direction. This is going to shrink as I'm walking away from the load. At some point, I'm going to hit this line at some point along the load, and I'm going to have a purely real reflection coefficient. And then it's going to go around and around. So this is what's going to lead to the impedance, sorry, the Smith chart being this circular graph. All right, so we're going to be going around as we moving away from the load. And we're going to trace this circle in the imaginary plane. So again, if you had like some distance d, so at some distance d away from load, you would end up with a phase angle of, so this angle would be phi sub L minus 2 beta d would be your total phase. Mean. So this phase total would be that, and then your amplitude would still be gamma sub L. Okay, so that's how this reflection, this line reflection coefficient changes as we walk away from the load, in distance away from the load impedance. Okay, it's going to have the same magnitude, but its phase is going to change. Its phase is going to change as we walk away at some point, and it's going to be just going in these circles. That's why you go from short circuit. If you had a short circuit at the end, you go from short circuit to open circuit, back to short circuit, and everything in between, all the impedances in between on the line. Okay, so now let's look back at the impedance and look at the impedance of the line, which we can also write as a real value, sorry, the impedance of the load, we can write as a real value plus an imaginary part. And we can say that if this is negative, if this is positive, it means inductive. And if it's negative, it means capacitive. So if I was going to draw this thing in its own complex plane, so this is the Z complex plane. This is the gamma complex plane. So this is the real part of Z, which is equal to R, and this is the imaginary part of Z. Which is equal to X. Okay, so that's what it looks like. So let's say I say that I'm going to restrict, I'm only going to look at, so only look at passive loads. Only looking at passive loads means that only R greater than 0 makes sense. Sorry. Why is that? So, like, does a negative resistance make sense? Have you guys heard of a negative resistance at any point for a resistor? We haven't heard of it, right? But you can get a negative resistance if you use a transistor. Okay? So we're just going to look at passive loads right now, which means I'm only going to look at positive R's. Okay, so that means this side of the plane. So I'm not going to restrict X, but I'm only going to look at positive R's for passive components. So that means we're going to only be looking at this plane. Okay, and then also this is capacitive when you have a negative imaginary value, you have a capacitance. When you have a positive imaginary value, you have inductance. Okay, so to recap where we are at this point is we defined a line impedance and a line reflection coefficient. So at any point along the line, we have those two factors. And we are looking at the behavior of the line reflection coefficient in its own imaginary plane, it looks like it's going to trace a circle. It's always, the circle's amplitude is always the load reflection coefficient, and it's just as I'm walking away from the line, it's going to be going in circles. So that's the behavior of the reflection coefficient. The behavior of the line impedance is that it's only going to be with a passive load, is that it's going to be somewhere in this right half plane. It doesn't have as clean a behavior or as limited a behavior as the reflection coefficient, which is just tracing this circle, but it's just going to be on the right hand plane. Okay, so those are the two factors. Okay, and so those are where we're at this point. And now the third thing, which we've also talked about, is those two things are functions of each other, right? So z is a function of the gamma. So z is a function of gamma, and gamma is a function of z. Sorry, I wrote this wrong. Plus. So these two are related together. So this z is a function of gamma sub z. So what the Smith chart is going to do, so this is just like I'm giving you guys a collection of random things, none of which is untrue. So all this, like I'm giving you these various like true facts. What I'm trying to do is to plot the complex, I'm trying to plot the impedance in the same plot as the reflection coefficient. Okay? I'm trying to move this z into this plane so I can draw them at the same time. So our Smith chart, what it's doing is it's drawing, it'll have information on, at any point, you'll have information about both the reflection coefficient and the impedance. And you can just sort of read that off the chart. And that's what we're doing. So the last step is, this is gonna really like be difficult to absorb, is we're gonna do a bilinear, it's like a, what do you call it, a $5 word, a bilinear transformation from z into gamma sub I. So we're gonna go from this, we're gonna take z from its plane into the gamma plane. And I can see you guys need a break before we do that. Could you guys use a break before we do that? Or should I just hit it and then we just break? Break time. Okay, let's get back together at 9:15. All right, guys, so here we go. Strap yourselves in. Just kidding. I just have to write this stuff for you guys, but you just need to worry about the end result. Okay, so we're doing this bilinear transformation of basically impedance, and the end goal is to draw, so end goal is to draw Z and gamma on same graph. Okay, so that's really all I'm doing. So Z I'm going to write that as a complex number, and gamma is also a complex number. And we know that this is 1 plus gamma of Z over 1 minus gamma of Z. So I'm going to rewrite this as Z is 1 plus, I'm going to basically plug this thing into here, okay, with these gamma sub Z's. So it's 1 plus gamma sub R plus J gamma sub I over 1 minus gamma sub R minus J gamma sub I. And then I'm going to just multiply top and bottom by complex conjugate of gamma. And I'm going to end up with 1 minus gamma sub R squared minus gamma sub I squared plus J 2 gamma sub I over 1 minus gamma sub R, just the whole thing squared, plus gamma sub I squared. And this is equal to R plus JX. So this is the real part of impedance. This is the imaginary part of impedance is related to the real part and imaginary part of the reflection coefficient using this equation. Basically, the solutions, you end up with like basically a couple of solutions to this. We're using this bilinear transformation, and that is gamma sub R minus R over R plus 1 squared plus gamma sub I squared is 1 over R plus 1 squared and gamma sub R minus 1 squared plus gamma sub I minus 1 over x squared is equal to 1 over x squared. So this one is relating gamma sub R, gamma sub I, and R together. So it's relating the real part of the impedance with the real and imaginary parts of the reflection coefficient. And this is relating gamma, the real and imaginary part of the reflection coefficient, with x, which is the imaginary part of the impedance. Okay, so the Smith chart is like the drawing of these two things. And these two things look like two circles. So are you guys familiar? Remember the sort of the circle equation is like x squared plus y squared is equal to r squared. You guys remember this kind of like general equation for the circle? So basically this, if you just think of this as an equation, it looks like, if I draw this if I draw it in gamma sub r, gamma sub I plane, this guy looks like a circle with the sort of the gamma r center being in r over r plus 1. It's centered at that point along this line, and along this line it's centered on 0. And the radius is 1 over r plus 1. And if I draw this guy as a circle on the same plane, it looks like on this axis, the center of the circle is at 1, plus 1. And along the imaginary axis, the center of the circle is at 1 over x. And the radius is 1 over x. So I have two circles on the reflection coefficient plane. They're both a function, one of them is a function of the real part of the impedance, and the other one is a function of the imaginary part of the impedance. Okay, so as r, so let me write what I just said down. So centers, or how should I do this? Let me actually do this. Let me move this guy over. So this guy is circle with center at r over r plus 1, 0, and radius 1 over r plus 1. And this guy is a circle with center at plus 1, x, and radius 1 over x. And it's a circle when I draw them on this sort of the gamma real, gamma imaginary plane. So it looks like two circles that are functions of the real and imaginary part of impedance. Okay, so imagine as I'm changing the real part of the impedance, the center of the circle is going to move. So the center of this circle, that's a part of the real part of the impedance, it's going to move, but the center is always, this part of it is always 0, right? It's always 0, but it's going to move in r over r plus 1. direction. Okay, so as I change R, that center of that circle is going to shift. And as I change R, the radius of the circle is also going to shift. So as I change my impedance, that R is going to like expand and subtract, but it's not going to go up above the imaginary axis. Okay, and as I change the imaginary part of my impedance, that circle is going to always be centered around 1, the real part of R. So that's, the circle is going to be always around R, but it's going to go up and down. That second circle is going to go up and down depending on the value of the imaginary part of the impedance, and its radius is also going to shrink and expand as a function of the imaginary part of the impedance. Okay, so I'm drawing, all I'm doing, this whole activity up to this point this morning was to be able to have a graphical tool where I can look at the reflection coefficient. So I'm drawing this graph is this thing. At any point here, I'm going to be having the reflection coefficient. Any point here, this is a reflection coefficient plane, right? So what I'm also doing there is graphically drawing as my impedance changes, how is it gonna, the reflection coefficient is gonna change? That's all. That's all activities based around that. Okay. Does anybody have a question? I mean, there's like a lot of work to get to this point. Yeah.
So
anyway.
On the chart, this would be it matching its impedance then?
What's that?
On the chart, so this is the center. This is when Z0 is, or the Z low is equal to Z0, and then that's open circuit, right? And this end.
Yeah. Let me draw it exactly.
So I'm just looking at the circles I'm seeing.
Yeah. Exactly. So let's look at a few cases. So that's kind of a good place to start looking at it. So let's look at, let's see, where do I have a few cases? So let's look at R is equal to 0. Which is a short circuit, which is short circuit load. Okay, when I have R equal to 0, let me actually draw it in a bigger graph here. So this is gamma sub R, this is gamma sub I. So when R is equal to 0, which means, so that's a short circuit, and R is equal to infinity is open circuit. So for R equal to 0, center of the circle is at 0, 0. So I'm reading off of here, just setting R is equal to 0. So I'm going to be center is going to be 0, 0, 0, 0, and I'm going to have the radius is going to be 1 over 0 plus 1. So if I draw that circle, see if it'll actually do it. Uh-oh. I'm not sure what to do with this. But anyway, imagine this was a circle that was, I'll try it one more time. I'm trying to center it on. Can't get it centered. But I mean, just imagine if it was centered, okay? Maybe I'm just better off drawing it not centered. Okay, so that's one circle, right? And let's say R is equal to infinity, right? So at r is equal to infinity, r is equal to infinity, center is at 1, 0. So if I plug in infinity here, I'd end up with infinity over infinity, or 1. And then the other place is going to be 0, so it's going to be at 1, 0. And the radius is going to be 1 over infinity, or 0. So that's going to be like a circle sort of centered around here, but it's going to have 0 radius. Just going to be a dot. Those are the two extreme cases of the real part of the impedance changing. So as for infinity, it's like a circle centered at 0 with radius 1. And at r equal to 0, it's a circle of radius 0 centered at 1 equal to 0. And as I go in, so there's all the numbers in between, right? Between 0 and infinity. So what I end up with is a bunch of circles that are changing their radius and moving in this direction. Okay, so I end up with like this, this, this. Okay, so they're sort of moving the center. So if I draw, let's see, if r is equal to 1, the center is at 1/2, 0. So the center would be here, and the radius would be 1/2. So that would look like, here we go again, very poor drawn circle. So this corresponds to, so this is r is equal to infinity. This dot here is going to be is equal to r is equal to 0. This guy is going to be r is equal to 1/2. And then I would have like r is equal to 2/3 is going to look like something like this. Not precisely drawn, it should be going through there, but you guys hopefully are seeing a pattern here. So this is kind of the same as I'm drawing the Smith chart, so it's basically these circles here. So like these circles are different values of the real part of the impedance. Okay? Also, guys, just remember that this is the, I know there's a lot going on here. This is the normalized impedance, meaning that I've divided the impedance of the load by the characteristic impedance. It's normalized. So like sort of the amplitude, the maximum amplitude of impedance in this case is just going to be like, basically normalized to that value. So, okay. So that's R, as R is changing, as the real part of impedance is changing. As the imaginary part of impedance is changing, then we also end up with different circles. So as X is changing on the same plot, so X equal to 0, we end up with something whose center is at 1, infinity, and the radius is infinity. So as the imaginary part of the impedance is changing, I'm going to have a circle that's at +1, 1 over 1 over 0, which is infinity, and 1 over x, which means it's like has a infinite radius. Since you guys aren't jumping up and down, I get the feeling you've already given up. Come on, guys. So that is a line. Okay? So if the load, so this is if x is the imaginary part of the load. You guys with me? So if the imaginary part of the load is 0, means the load is purely resistive. Okay? I'm going to get a line. I'm going to run out of colors here pretty soon. That's going to be like running like that. It's an infinitely long line. Gonna have to figure out who I'm gonna pick on here. Claire. If I'm here, what's my load impedance? If I draw my load impedance here. What's that? It's just real, right? So it's a resistor. You immediately know it's a resistor. What's the value? So it's the, let me just tell you this, it's the intersection between the X and the R line. So if I'm here, there's an R line, that's the circle, that's intersecting the X equal to 0 circle. That intersection here says your imaginary part is purely 0 and your real part is 1/2. So you have the load is a resistor, and its value is half the value of the characteristic impedance. Does that make sense? Kind of. So if basically, again, this is a graphical tool where at any point, so I picked that as like a sort of an easy to think point somewhat, is at any point I'm looking at the intersection between these two circles. Again, I've drawn the X, I've only drawn one circle. I just wanted to get you guys sort of thinking about what I'm drawing. But if I keep drawing other X's, so X equal to 0 is a purely real load. So now, but I can go to X equal to infinity. And then I'm going to get a circle at center 1, 0. And radius of 0, so that's also a point. X equal to 1, I'm going to have a center at 1, 1, and radius 1. And x equal to -1, I'm going to have radius 1, center 1 -1, radius 1 also. So I'm going to have a bunch of like circles running around there. But they're kind of, those circles, if you look at where those circles are, they're kind of like around here. So if I draw just part of those circles, so the first one I drew was this guy, right? This guy along the line, which was x equal to infinity. If I draw this guy, its center is going to be like, so like its center is going to be like here somewhere maybe, I guess, right? So imagine if I just draw part of it, the radius. Its radius is going to be like, let's see, like, it'll be like that. And if I draw this guy, so like imagine me completing the rest of the circle around. And then this guy, imagine my center is here, and I'm going to draw that circle, but I'm just going to draw where it overlaps with these circles. The maximum value of these circles is 1. Maximum value of these circles is 1, right? Because that's where r is equal to infinity. So I'm just going to draw that overlap over here. So those are going to make circles, and if I just draw the part of the circles that overlap, they're kind of going to look like this, like that, that. So I can keep drawing it for different values of x. And again, these are, so I have 2 circles, one for circles with varying imaginary part of the impedance, sorry, the real part of the impedance, and then circles drawn with the imaginary part of the impedance. But I'm just drawing part of those circles that are overlapping. Okay, so that ends up being this Smith chart. So I have these, oops, I can't draw on that, but like I have these circles that are changing that are the real part of the impedance changing. Okay, so they're like doing that as that value is changing. And then I have circles where they look like arcs because the circle center is up here, down here, whatever. So they look like arcs, but they're circles of the imaginary part of impedance changing. Okay. Guys good? So just a graphical tool now, and a way to, if I sort of draw how we'll show a couple of examples of how this gets used. Quite a few, like there's a bunch of different ways this gets used. But you guys can see how we're gonna draw a point here which represents an impedance, a particular impedance. And then we can see how that point, we can draw a line about how that point moves around as you move away from the load, as you go along the transmission line. So then from then on, you can just read off what your effective impedance is looking into the transmission line just by looking at the graph and not needing to calculate those tangent, delta, whatever. And it's also gives you like a feel about what's going on. Okay. All right. What else do I want to say? All right. So let's look at a couple of the applications of this transmission line. Whoops. So the first application is finding the line impedance at any point along the transmission line. So case 1 is find line impedance at any point along the line. Given a load impedance and a characteristic impedance. So this is exactly the same problem we would sort of, I don't know if, well, hopefully you guys remember, I don't remember the equation, so I have to like look it up. This line impedance equation was Z sub 0, z sub L plus J z sub 0 tangent beta L over z sub 0 plus J z sub L tangent of beta L. So this is the same, what we're about to do with the Smith chart is the same as solving this equation for the different values of L for different values of ZL and Z0. So instead of doing this, we're going to do this with like a Smith chart. Okay, so this is, I guess you'd call this a complicated formula. So instead of solving this, we're going to use the transmission line. So now I'm going to assume, by the way, for all this stuff, that Z0, Z sub 0 is real, meaning that it's a lossless transmission line. So it is this is the visual for this problem is I have a transmission line with impedance Z0. It has a load Z sub L. And then I'm going to look at different points along this line and at each point figure out what's the input impedance is. So to use the Smith chart, you still need Smith chart. Still need somebody to give you, or you need to decide Z sub L, Z sub 0, lambda, Z. Somebody still needs to give you these numbers, right? The load impedance, the characteristic impedance, where you are along the transmission line, how fast, what's the frequency of your source, okay? So, let's see. So let's say we're trying to solve this problem, right? So let me draw this, actually copy over this transmission line. Oops, am I going to be able to do that? Let's hope. So what you, by the way, what you'd normally do, I guess I could do it now, but I'll do it on this one. What you'd normally do is you would, let's say if you were going to do this by hand, you would like print out a copy of the Smith chart, which is you just get downloaded the PDF on the web, okay, and basically draw. You wouldn't be drawing like I'm drawing with the circles and stuff. This is like this blank pages for doing that. You start with this, and you start writing down these values of impedance and L and seeing how they move around this thing, okay? So you can either buy these, I guess, online or just print them out. It's probably easier to do, okay? And there's different measurement tools that, when you hook up to, if you, like for example, they have something like if you actually were going to measure the input impedance of a transmission line, what would you do? It's like not easy, right? You like have to, what people would do is actually they make a sample of that transmission line and so you'd make like, let's say on a printed circuit board, you want to see what the impedance looks like along that line. What you'd end up with is you'd make a bunch of copies of that transmission line, and at different lengths away from the load, you would put up a slot to stick like a probe in to measure the voltage at that point. I'll get into that, but anyway, so there's it's like you gotta find some way of doing these measurements, or you'll use the transmission line. I mean, sorry, the Smith chart. Okay, let's just do it. Sorry, I keep going on tangents, but let's just stick with this for now. So again, imagine that this is the real part of gamma, and this is the imaginary part of gamma. And if I was gonna draw the reflection coefficient of just gamma sub L, what it would look like is color. Running out of colors. Let's draw it in black. Let's say if I was at this point, okay, if I was, imagine this point here, let's see. I would be at this is the amplitude of this is gamma sub L, and it's going to be at some phase value, whatever is the load. So this would be, the starting point. Let's call that A. And let's say this is 1, 1, the value of this thing. Actually, let's take it. Okay, sorry guys, let me do this step by step. So let me write the steps down for you guys. How do I do this? It's hard to draw. Let me really need 2 pages. Stuff. This over. So step 1, want to normalize Z. And the normalized Z is Z sub L over C sub 0. And that's going to give you a real part and an imaginary part in a general case. Like in the problem you guys are going to have in your problem set. It's going to be a real part and an imaginary part. It's going to be a resistive part and an inductive or capacitive part. But the first thing you do is to normalize it. Okay? If this is a positive value, okay, means you have sort of like an inductive type of situation on the load. If it's a negative value, means you have a capacitive type of situation on the load. But either way, you normalize it. Okay? Now let's say step 2, you draw that point. So draw the point at the load on Smith chart. I'm just going to call it SC. Okay? Let's say we assume that initial point at the load is 1, 1. So R is equal to 1, X is equal to 1. Okay? That corresponds to this Z bar being 1 plus 1J. So Daniel, I'm gonna pick on you. Haha. Imagine if if I told you the characteristic impedance of this line is 50 ohms, right? What would the value of the actual value of the load be
You have to
with this?
multiply 1 by 50, so it's 50 plus 50J.
Yeah, so you'd have, so the actual, if my characteristic impedance was 50 ohms, means that the load I have a 50 ohm resistor and like a 50 Henry inductor. So would you end up with 50 plus J50. 50 inductor at the frequency I'm running at. Okay. Okay, so the next thing, so the next step, so this is step 2, step 3. Is, so I'm going to draw that. So I'm going to draw this point pretty thick. Let's say if it was here. Let's say this was 1, 1 as my starting point. And let's say I call my starting point A. So at load, which is call that point A, which is that guy. That's the first thing I'm going to do.
I have a question.
Yeah.
Why do we assume that R is 1 and X 1? Do we always assume that?
Can you say that again?
For the case of our client, do we always assume that R is 1 and X is 1? Why do we make that assumption that R is 1 and X is 1?
Oh, I'm just saying, let's assume that's the case.
Oh, but it could vary based on the plug and case.
Yeah, exactly. It depends on the load value. Yeah. So this basically ends up being your starting point is your impedance at the load. And as I look through my impedance, walking away from the load, this point is going to change. It's going to start, I'm going to have like a line along this Smith chart that's going to tell me how that moves as I go away from the load. Okay? So this is just assumption of R equal to 1, X is equal to 1. So basically, if I draw this point, A, I'm going to have a it's going to have a amplitude and and a phase. So this is phi sub L. So on this chart, the maximum value is so the maximum value of gamma sub L, the maximum value of the load reflection coefficient, the maximum value is 1. Because remember, this is Z sub L minus Z sub 0 over Z sub L plus Z sub 0. You guys with me? So that was always the case. The maximum value is 1. Because when you think about it, it makes sense. If you have a passive component, you can't have a reflection that's like higher amplitude than what you transmitted. Like at most, you're going to reflect back the same amplitude. Like you would have to have gain if you have a reflection coefficient higher than 1. Okay? And that's going to be along this circle. Okay, so if I call any point along the circle M, let's just call, I'm going to do it over here just so it's easier to draw. I'm going to have, a sort of a distance between O I'm going to call the center O, by the way. O. So physically, I can go physically measure this distance, and I can physically measure this distance. I'm talking about physically measure it on the chart. I can say, okay, I drew that A over here, and that's like, whoops, and that's like, so you guys can't see that. So let's say I draw my A here. Okay, so OA, I can say, well, physically, this is like 8.5 by 11 sheet. Say that's 2 centimeters, okay, on my chart. And then M is over here. Let's say on my chart, OM is like 4 centimeters. Okay, so the amplitude of OA, I can physically measure it and call that amplitude is, that gamma sub L is OA over OM. Let me show you what I mean by that. So gamma sub L, so this guy is just going to be physical length of OA, which is this line. So basically the ratio between this line and the line from the origin to the end of the circle over OM. So got to remember this is a graphical tool, and basically kind of as the first step in the graphical thing is it's allowing you by, so at the very first point when you draw the impedance, you put that impedance point, you can read the reflection coefficient just from the amplitude reflection coefficient just from where that is. Does that make sense? Just measuring this distance. You don't have to basically calculate what it is. You can get that value. Yeah, then.
And just whatever A is perpendicular to it in the opposite direction?
It doesn't, it's a radius, so it could be like here or here. I'm just saying like
you're saying
from
like-
any point on the
Okay.
R is equal to 1
Yeah, I understand.
circle. You guys with me? So you just measure what it is and then that's the value. Okay? It seems kind of stupid because, so this part is like the Smith chart had 2 components. One of them is a graphical tool and the other one is a way not to do these calculations. Okay, so we're using really simple cases where, we're talking about open circuit, short circuit cases, impedances and all this kind of stuff. As you'll see in the problem set, as soon as I make that a little bit complicated, it gets like difficult to start doing the calculations at every point. I don't know if that makes sense or not, but hopefully if you solve the problem, you'll see it. So now you can just sort of read it off. Okay, so that's the first nice thing, but it's the beginning of our multi-step journey. Okay, so. Okay, now as I move away from, so remember that as I move away from the load, if I'm going to be drawing my reflection coefficient, this guy, as I move away from the load, this is going to take a circle around. The amplitude's going to stay the same. And just this phase, the total phase angle, it's going to change as I change beta. As I'm going to change L along the line. So step 4 is I'm going to determine how much I have to move, right? So determine or how much to move along transmission line. Let's say that distance is L. Okay? So beta is a given. So my total distance, so what I want to do is calculate 2 beta L. So that's going to be 2 times 2 pi over lambda times L. This is all in radians. So whatever that is. And I'm going to do, this is like so I'm going to move that much in a circle in a clockwise direction. So I'm going to go like that. Let's say it's this much. So this is going to be 2 beta L radians. And this is going to be my new point, B. And so now I'm going to read my new impedance at this point, B. So to remind you guys what we're doing here is we have a transmission line. With some kind of a load, Z sub L, characteristic impedance Z, and it's going to have, so at the initial point, I'm going to take the impedance of the load, draw it on my Smith chart, and that just looking at the amplitude of that line, it's going to tell me my reflection coefficient at the load. Okay, that's this point A, and this distance is the amplitude of the reflection coefficient. And this phi sub L is the phase of the reflection coefficient. As I want to look at different points, what the impedance is at different points along this line, I take the length, multiply it by 2 beta. As I'm walking here, take the length, multiply it by 2 beta, and that tells me how much I'm going to be traveling, how much my phase is going to change from this starting point in the clockwise direction. Okay, and I'm going to land at some L, whatever if somebody told me, hey, it's a centimeter away from the load, what's my impedance at a centimeter away from the load? You can either calculate it with this equation, or you can draw that, send them to beta L over here and read the XY value of this point, and that gives you the impedance at that new point. Exciting? No. Yes, come on, it's exciting, guys. Jump up and down, be excited. So again, like right now, do you guys see what's going on here? It's just a tool, a graphical tool that's immediately, once you know the impedance, you get the reflection coefficient at any point in your transmission line, and as using it in different ways as you move along that transmission line, you can see how the impedance is changing. Okay? Again, these days, it's not that difficult to plug this into your Excel sheet and just put in different values of L and get the input impedance, right, as you're walking along L. So seems like you're doing sort of a lot of work here with this graph. Like, why am I doing this? Well, this also gives you a visual tool about how the impedance is changing as you're going along that transmission line. Let's, for example, say, if I want to go work backwards from it and say, okay, at what point along that transmission line do I have a purely resistive impedance? So if my question is, hey, I'm going to use this transmission line at this wavelength to just get something that doesn't look inductive, something that doesn't look capacitive, okay? Where do I tap into this transmission line to get that, right? What I would do is draw this arc and figure out where it crosses this axis. This is an axis where I have a purely real impedance, okay? So at whatever beta L I got to this line, that's gonna look like a purely resistive load. So I can go, okay, that's at 2.23 centimeters, and that's how long I'm gonna make my transmission line with this load to look like a purely resistive load, okay? If that's what I want, or pure resistance, if that's what I want. Or let's say I start with some value here, and I wanna say, look, I want a capacitive load of a certain value, right? I can see how far I need to make that line. Remember, this bottom part is capacitive. This top part is inductive. If I'm reading impedances, right? If I'm reading impedances, these are positive and complex. These are negative and complex. So this looks like a capacitive load. This looks like an inductive load. And this looks like just a purely resistive load. So if I want to say, okay, I want a particular capacitance, okay, I want it to be here. That's how long this line needs to be for me to have what looks like a capacitance at that frequency. Okay, so it's it's a graphical tool to see what the behavior of your line looks like. Okay. You guys have any questions about that? I know it's a lot to take in. And you're doing this all, I'm kind of drawing the Smith chart, but you would always start with this guy, okay? And start, the blank sheet, draw it along that line, draw how it changes, and then now you can sort of read off, depending on where you want, what the different lengths are. So that's use 1, application case point 1. Okay. There's like a bunch of uses. So now let's look at another case. Okay, like now we want to see, let's like actually look at what yeah. Okay. So now we want to step 4. Is we want to go back to sort of get the multiply Z bar by Z naught, and you get the actual impedance at whatever point L you have. Okay, so along these lines, sort of like to help you with drawing this, there is a, should be, let's see, I can't. Let me try doing this. Let's see if I can just dump this into my, no. Just copy it. Oh, nice. Oops. Can't quite get it right. Okay, great. Now I can draw on this. Let me make it smaller so we can zoom in. This might not really help because it's okay. Whoops. Okay. Let's look at this now. So there's a line, a circle up here. It's this guy here. It's going all around. And I don't know if you can read it. It's really hard to read. It says wavelength towards generator. Okay? Wavelength towards generator. So what you would do is, let's say, again, in this case, you would this how should I put this? Well, let's do it, and then I can go backwards and try to explain it, because I'm trying to these are weird concepts. So again, just remember this is a graphical tool. Okay, so what I'm about to say next has no physical correspondence. Okay, this wavelength towards generator has no, it just is something that is going to help us get from point A to point B. It's a drawing tool. Okay? So there's this circle of up here, and that is the WTG circle. It stands for wavelength towards generator circle. So there's no like physical meaning. So it's not like some new thing I'm giving for you guys. So let's, for the sake of discussion, let's say I had my, this was A. There's not an easy way to do this, is there? A. This was my initial point A. I would draw a line. I would extend the line of the OA along the same line. I would just extend it out. And read the value on the WTG circle. Okay? It says heck does it say? See, let's for the sake of discussion, let's say it says 0.35. I don't know. Oh, let's say it says 0.35. You guys with me? So I'm just reading that value, whatever that says. This number is just this guy over here. Okay? Now let's say I'm moving a distance of, and assume, move distance of L over lambda away from the load. Okay, let's say that is 0.2. So L is 0.2 lambda. So I'm going to add 0.2 to 0.35. Say it's 0.55 lambda. And then let's say that corresponds to a line that's like here for the sake of discussion. Okay, so I'm just basically reading the value along this curve where it says 0.55. I'm just sort of making up numbers here, guys. This isn't like actual numbers reading off. So you would go, okay, from here to here, that's where my B is going to be. It's going to be along that line. So this is going to be, let's call this B prime, let's call this A prime. This guy give you guys a headache? So what I'm doing is, I'm trying to figure out how long to make this thing. I'm trying to figure out where B is. Draw B in here. This length stays the same because it's just going to rotate around the axis. The reflection coefficient's amplitude stays the same. And it's just going to be going in a circle around as I move away from the load. Okay. So all I'm doing is I'm like reading the value here, which gives me that angle. Okay. I'm adding this L in the form of lambda to it, and ending up at another point in the circle, and figuring that's the new angle, but the actual amplitude stays the same. So I'm going to end up there. At my new position, L is equal to, at this new L position. Daniel, you have a question?
Yeah, why do we use the wavelength towards generator instead of wavelength towards load? What's the difference between the two of those?
So it's exactly like that. So wavelength towards generator is, well, that's a really good question. Let's see. So in the olden days, we had the load always. The olden days, the signal generator, it was called a generator. So instead of the voltage source or the source, they called it the generator. And what we're doing is, the way our approach has been to figure things out at the load impedance and then go towards the generator. So it's starting from the load, going away. When you're going away from the load, you're going towards the generator. And so it's like the distance is given in wavelengths towards the generator. And if we'd gone the other way, if we were going towards the load, would be wavelength towards the load. Does that make sense?
So when we reference like Z to 0,
Yeah.
we do it that way, but if we did Z to 0 at the generator, we
Goes-
do wavelength to load.
Exactly, yeah. Any other question? Clear? Ha ha ha. Okay, let's see what else do I have. Okay, let's look at another application of Smith's chart. Number 2. So this second application is, remember again that if we had a situation where we had if Z sub L is anything other than Z0, I'm going to have standing waves on this transmission line. And they're going to have maxima and minima. Maximum values and minimum values as I go along this transmission line. Okay, so what we can use this for, this tool, is to find Vmax, Vmin, basically the locations, find locations of Vmax, Vmin on the transmission line. Sorry, was there a question? Hand up? No. So in this case, you would end up with a standing wave. So if I was going to write the voltage here, it would be like that, and it would have maxima and minima. And the reason, again, it's a standing wave is you have at any point here, you have a transmitting wave going this way and a reflective wave going this way, and they're going to either sum up constructively or destructively in different levels, and so you end up with what looks like a standing wave if you go and probe the voltages along that line. So basically, again, if I draw the Smith chart, so let me actually go through the procedure. So what I would do is step 1, so 1, I would find, this is, you always do this, is the Z sub L bar is Z sub L over Z sub 0. Then 2, find location, basically find Z sub L bar at A. So draw like a circle with that radius. So if I was going to do a transmission line, a Smith chart, it would be like, these would be the lines. So I would find the location of A, and then for the absolute value, the reflection coefficient at that point would be, so this is drawing Z bar. The absolute value of the reflection coefficient would be the distance from O to A over O to M. So M is any point along the furthest out circle in the Smith chart. That would be the actual amplitude of the reflection coefficient. At Vmax, the phase is equal to 0. So basically what the reason for that is V line is phase equal to 0 is V0, the amplitude of V line is equal to V0, amplitude V0, 1 plus gamma L. So that's maximum at, so remember that, let me take a step back here, guys. So the voltage of the line voltage was gonna be V0 plus, the amplitude of that is V0 plus amplitude of 1 plus gamma L e to the J2, J2 beta L plus phi. So this maximum happens when this guy goes to, this whole thing goes to 1, is when this guy maximizes. So it's when this value equals to 0 is when I get a maxima. So that's why I'm saying this phi, which is, so phi is 2 beta L plus phi sub L. Call that phi. So when phi is equal to 0, e to the J2 beta L plus phi sub L is equal to e to the J phi is equal to 1. So that's maximum line voltage. And when phi goes to 0 is actually when, so you've drawn this circle here at this point. Okay, that's a circle that's centered around 0. The magnitude is the reflection coefficient. And the circle, along the circle where you are is how far you've moved away from the load at a from a starting point. The first maximum occurs when you hit this point. That's when phi is equal to 0. The total phase is 0. So you went from some phi here to 0. So basically what you do is you want to figure out how much you traveled away from the load before you get to this point where you're on this axis, to get the maximum value. So what you do is you draw this line to the, so this wavelength towards generator line on the outside dimension. And then you figure out how much you have to move to get to here, and that ends up being the location of the first maximum, the first voltage maximum. Okay. So let's say for the sake of discussion, when you drew this line and you got to this to this wavelength toward generator line, this is an example. It ended up being, at this point, it was 0.25 lambda. You read it off and it was 0.25 lambda, so assume wavelength TG value at A prime is 0.25 lambda. And then this value for, sorry, let's say this is 0.15 lambda. I'm sorry, guys. Say 0.15 lambda. Because the value of this WTG right here is actually 0.25 right here. So you want to find the difference between, let's say you'd read out, again, I didn't read this quite right, so this was 0.15. Want to see what distance this is. Okay, that distance is 0.25 minus 0.15. So L is 0.25 lambda minus 155. This WTG 0.25 lambda is basically right here at this point. So if this was 0.15 lambda, I would have to move away from the load by 0.1 lambda to end up here. And that's the location of first maximum in voltage. And then if I keep going along this curve away from the load, so first I end up from here to here, it's my first maxima. And I keep going along this circle till I hit this point. This is my first minimum. Okay, and if I calculate the distance between the WTG point from here to here is how far I need to travel back from my load to hit my first minimum along this line. And then I can move another distance lambda over 2 to get to the next maxima, and another lambda over 2 to get to the next minimum, and so forth. I'm just gonna have a bunch of minima and maxima as I walk away from my load. Daniel, you look like you're...
I was just wondering, like, on the test, are you expecting us to, like, print out a sheet and do this? Because I don't have a compass or calipers. So,
No,
or do you just want
compass,
us to
not
do
calipers.
do you just want us to use the standing voltage and the line equation to calculate these stuff? Or do you want us to show us, like, roughly that we know how to do it?
Good question. Is anybody gonna use like pencil and paper for this, or are you guys gonna use like using MATLAB? You gonna use paper and pencil? Paper and pencil. How would you do this with paper and pencil? So you need to, so where would the, wait, where would the calipers come in?
To get the distance, if you want to get accurate. 'Cause you
Yeah,
have to
yeah,
find that,
yeah.
and you have to find the M distance,
Yeah.
and you have to divide it.
No, I don't need to make it accurate. You know what you can do? Okay, I'll come up with something.
There's a code, but like, I don't know how it works.
What's that?
There's a code on the book for how to do a Smith chart on the line,
Yeah,
but I don't know how you like find a point and do it. It
yeah,
just generates a chart.
yeah. Might just have to draw it by hand, I guess. So that's a good question. I'll think about that. I'll think about how to do it on a paper and pencil. But it's a good question, though. I guess we're in a different age. You guys don't have the. You guys have rulers, though, right? No?
Use a string, I guess.
String. You could use a string. I was gonna say use a string, but I didn't want to get slammed down. All right. Good question. So guys, we're at 10:45. So I keep asking the same question. This is the end of the class, right? Yeah. So we didn't make it as far as I wanted to. So what I'm gonna do is record another 2 or 3 applications of Smith chart and put it online for you guys to take a look at for the midterm. But they're all sort of doing the same thing over and over again. They're going through this multi-step procedure of figuring out what the Z sub L sub bar is, where your starting point is along these circles on the load, and what happens as you move away from the load, and using that to get your reflection and impedance is. So, but I think I have to think carefully about what kind of problems to give you guys to not let your lack of equipment get in the way. Lack of primitive equipment. So it'd be like going to one of those classes where you have to start a fire with a couple of sticks. So think of it like that. No, I'm just kidding. Okay, guys. So there are problem sets are online. As I know, Daniel, you worked on the first problem set. I still owe you an answer
Yeah.
from one of them. Has anybody looked at the second one? I just went up. You already looked at it? Did it make sense?
Yeah, I did.
Did this put this thing in context a little bit?
Yeah, it made sense looking at the problem set first and then seeing.
And then look in this first, yeah, okay. Yeah, I'm hoping as you guys look at the problem, you'll see what this gets used for. Okay? And it looks like a real primitive thing, but it is used still a lot, not for the absolute values necessarily, but for seeing what the relationship looks like as you're going through. Okay. All right, guys.